Alright, so now we're finally in the last section, which is bit manipulation, and we have the first one, which is number of 1 bits. Now let's go to this problem, and it says number of 1 bits. Write a function that takes the binary representation of a positive integer and returns the number of set bits it has, also known as the Hamming weight. Now what is this all? Hamming weight, let's go and Google search this, and it's saying so write a function that takes the binary representation of a positive integer, okay, binary representation of a positive integer like this, and returns the number of set bits it has. Now what is a set bit? A set bit refers to a bit in the binary representation of a number that has a value of 1. So set bit means 1, okay, and also known as the Hamming weight. Okay, so I believe it's like binary representation of 1 plus 1, or maybe like this. I mean, what do you mean by this? So what is the Hamming weight? The Hamming weight of a string is the number of symbols that are different from the 0 symbol of the alphabet used. It is thus equivalent to the Hamming distance from the all 0 string of the same length. Now over here we have a string. This is 1 1 1 0 1. How many set bits are 1? 4. So over here we have 1 1 1 0 1. I think it's like 4, and then over here we have 0, and then over here we have 10, because these are all non-zeros, and whenever, so 3 4 5 6 7 8 9 10, and that's why Hamming weight is 10. So essentially that is the goal here. The Hamming weight of a string is the number of symbols that are different from the 0 symbol of the alphabet used. It is thus equivalent to the Hamming distance from the all 0 string of the same length. For the most typical case, a string of bits, this is the number of ones in the string, or the digit sum of the binary representation of a given number, and the I don't know, L1 norm of a bit vector. In this binary case, it is also called the population count, pop count, sideways sum, and a bit summation. Now, the input binary string 1011 has a total of 3 set bits. Now, input was this, right, which is 1 and 1, which is 11. And then this is how you represent it in binary. So we have 1 and then 2 and then 4 and then 8. Okay, then it has a total of 3 set bits, that's why. Now this is 128 in decimal. So that takes the binary representation of a positive integer. Okay, I understand now. It first takes a decimal number and then it will convert it into a binary number. Alright, so now it's a binary, and it will check the number of set bits, and then it will just output them. So the input binary string, it has a total of 1 set bit. Now this is a number in decimal. It will convert it in binary, all right? And then it will check all the number of set bits, and then it will return the number of set bits, right? A total of 30 set bits. How do we calculate this? Now, the constraints is that we have the n. So n is the number, right? So the n is the decimal number, and it should be in between 1 and 2 raised to the power 31 minus 1. Follow up: if this function is called many times, how would you optimize it? So, seeing this question in a real interview, what we're going to do first of all is we're going to calculate it with a really classical solution. And first of all, let's go here in class solution and public in Hamming weight int n. I'm going to go and maximize this a little and just put this on the side like this. Okay, so the thing is that we have something over here which is the unsigned, 32 underscore 2 tn. So basically we're using a decimal number. Whatever is coming in here is a decimal number. We have to convert it into a binary number first. Alright? And then we have to basically count the things. So one solution over here is, you get the count and put it as 0. You want to count the number of ones, right? So we basically put it like this. We count the number of ones through this. We go through a while loop, and we say while n is greater than 0. I'm going to reduce it to 0. So I'm going to count the count, and then we're going to add this thing, which is the n, and then ampersand 1. This means the bitwise AND operation, alright? And we get the bitwise AND operation, we add it with the count, and we add the count like this. And we keep going until we make a right shift operator. So this thing over here, which is, like extraction, and we put the equal and 1. So we're making right shift by 1 all times. And until we have 0, we could now essentially return. After the while loop would have a count that would indicate the number of ones. So if I could run this code, control and comma, see if it works. Okay, we got a wrong answer here. So in case 2 worked, number is 11, output is 1. What we get, well, actually it should convert it first and be 3, right? In case 2 it worked because number was 128, output was 1, and expected was 1. In case 3, it's basically number is like this, output is this, expected is this. Okay, we got a wrong solution here. We might have to change this up. So we have this count, and we have to basically find that. If I could actually convert that to what we need is basically an unsigned int 32. I think this is basically the decimal number, and then when we convert it, we get the right solution. Right now it's not going to work because the type is wrong, right? So we have to convert this into a binary number first. Okay, so convert into a binary number, and then we have to do this operation. Now, how do we convert a number to a binary number? All right, so first of all, let's say let's go here, say we want to first convert the number to a binary number, and then count all of the ones, okay, or set bits. So if I talk about the problem here again, we had this result, and if you remember, it kind of like gets the number, and I guess it just counts some sort of like ones for it, like okay over here. Okay, so it's a complete wrong solution. Let's see what it does over here. So okay, now it says over here, that's the interval problem. Okay. The provided solution attempts to count the number of set bits with value 1 in the binary representation of the integer n. However, there is a precedence issue in the count. Count is equal to count plus. Due to operator precedence, the bitwise AND operation is evaluated before the addition plus operator and leads to incorrect results. To fix this, you need to add the parentheses to it, ensure that the addition operation is performed before the bitwise AND operation. Here's the corrected version. Okay, it's saying first of all have the count and then just have the brackets in it. So I don't know. Let's see. Add this bracket over here, and then control and comma. Oh, now it worked. So it was a precedence issue actually. Okay. So this one was one solution to it, where it counts the integer. So I'm just want to actually explain. So basically, it was. However, there's a precedence issue in the line count is equal to count plus and add ampersand 1. Due to the operator precedence, the bitwise AND operation is evaluated before the addition operation, which leads to incorrect results. To fix this issue, you need to add parentheses to ensure that the addition operation is performed before the bitwise AND operation. Here's the corrected version of the code. Now, can you explain the above C++ code, because we want to understand it, right? Now, let's get the explanation for this. Let's break down the provided C++ code. So we have this entire solution, right? What is it about? The code is counting the number of set bits, bits with the value 1 in the binary representation of an integer n. Here's a step-by-step explanation. We have the function definition, we have the initialization, we have the loop, we have the bitwise AND operation, count update, write shift, and return count. So essentially, if we look at this function definition, we have the code defines a class solution, okay, which presumably contains a solution to some problem. Inside this class, there is a member function hamming weight, which is this one, okay, which takes an integer n as input and returns an integer, okay. So initialization, the variable count is initialized to 0. The variable will be used to count the count basically used to count the wait a minute, this variable will be used to store the count of set bits in the binary representation of n. So it's going to count the set bits, right? The number of set bits in the binary representation of n. Now, loop. The code enters a while loop with the condition n greater than 0. This loop continues as long as n is greater than 0. Inside the loop, we have bitwise AND operation, and so basically we convert this into a bit here. I was like asking, like, when is the number converted to a a binary number? Right now, it's a decimal when you look at n. But when you use this bitwise AND operation, it converts into a binary, extracts the least significant bit of n. This operation makes out all bits of n, masks out all bits of n, except the least significant bit. If the least significant bit is 1, the result will be 1. Otherwise, it will be 0. Now, the count update. The result of n ampersand 1 is added to the count. This increments count if the least significant bit of n is 1. Write shift. Now, this is write shift where n, and then we have the extraction operator equal to 1. Write shifts n by 1 position. This effectively discards the least significant bit of n, shifting all other bits 1 position to the right. This process continues until n becomes 0. And then we return count once n becomes 0. No more bits are left. The loop exits, and the function returns the final count of set bits stored in count. So, it would, to summarize the code, iterates to each bit of the binary representation of n, counts the set bits, and returns the total count. This technique is commonly known as the Brian Kernighan's algorithm for counting set bits. So you kind of like understand the whole process here. If I could actually just visualize it one more time so that you could finally understand the solution, is first of all, we get a number. Suppose we have a number like let's look at the first example here in the solution. We have the first is 11, right? So if we look at 11, 11 is a decimal number. When we want to convert it into a binary number, we have to basically convert it like this. So if you look at the decimals, we have 1, then we have 0, which is on the 2th position, and then we have 1, and then 1. So this means it's 11. So we have 1, and this is 2, and this is 4, and then this is 8. You kind of understand like how decimal systems work, right? So 1 plus 4, which is 5, and 5 plus 8, which is 11. No, that's not right actually. Where 8 plus 4, which is actually 12, and then we have 13. Yeah, so we basically did it wrong here. This is the representation for 13. Let me give you the representation for 11. So we have 1, 1, 0, and then 1. If we look at this one, which is 1, 2, 4, and then we have 8. We look at this properly, and we see that we have 8 plus 2, which is 10, and then we have plus 1, which is 11. Now this is the binary representation for 11. If we look at this binary representation, we have this right shift operator. When we use this right shift operator, you already know how it works, right? So we have the right shift operator that goes like this. It looks at the least significant digit. This is the most significant, which is right here. The most significant means the most weight, and the least significant is the least weight. So it looks at the 1. It checks out whether it's a 1. So it uses the bitwise AND operation. It uses the n, it uses bitwise AND operation, and it basically checks if 1 is with 1. If it is, it returns the count, and it would just increment the count within the count, thing. So it would just add the count actually. So count is equal to count plus whatever this number is. If it's it will add a 1 to it, and then it would basically right shift it. So it would right shift it by 1, meaning this would be discarded, and the next time we look at it, it would be this one. Okay, and then it would add this, so it would basically come in the count as 2, so it would just increment the count as 2, and then this would be discarded after the right shift, and then it would look at this. Well, it's nothing, so it would be discarded again, and then it would look at this one, and that could be 3. Then the total count would be returned after the for loop, which is 3. And that's exactly the solution here, which is 3 output, and this is the Brian Kernighan solution. One other way to approach this is basically you have the count, and then you have this while loop is greater than 0. You have this count operation where you could actually have count is equal to count plus, and then you have this operation. But one other thing, what you could do is you could just write it as like this. So you have this thing. It's just a shortcut. So plus equal to this. This means the same thing with count, and then same operation, same thing. So essentially, this is the solution for the Brian Kernighan's. One other way to do this actually is we have another approach where you could actually, instead of the right shift operator, what you could do is you have the count, and you make sure that the number is valid while the number is valid. You could essentially have the number do an basically the number could do a bitwise AND operation with n-1. Okay, what this means is that it's going to keep doing it until the number becomes 0, and then it would just keep incrementing the count. This would do the same exact thing if we look at the comma. I mean, if I run it, if I run using control and comma, it would basically work the same way. But you got my point here, that it basically gets the bitwise operator for the n-1, and then it adds it. I mean, it just continuously checks, and then increments the count whenever this happens, and then we return the count. So this way or this way, which is this, both seem valid. All right, and I like this one. It just looks better with both are okay and both look good, but this one you could kind of understand that's n greater than 0, and then we have count plus, and then we have this bitwise AND operation where we get the 1, and then we add it with the count, and we put in the count, and then we right shift again and again and again until we have the count. Both were good solutions, and comment which one you liked. So that's it with this one.